и оно существует, а переименовать не такая уж проблема.
Ну ладно. В общем, я написал, раз вышло.
Я в прошлый раз еще раньше вас об этом написал.
А, ну хорошо, ну, в общем, самое главное, что...
Я еще в середине лекции это обнаружил и уже написал.
Да. Вот написано скоро, я его уже спустил. Все то же самое будет?
Сейчас я просто зайду на канал Матфак и посмотрю, что там вообще транслируется. Так, да, то же самое. Но это ни я, ни вы не знаем, как это исправлять, поэтому пусть оно транслируется куда-нибудь, а там разберутся.
Ну, оно куда-нибудь будет транслироваться?
Но оно на Ютубе есть, просто это Гусева Cat Surfaces, но оно есть.
Ну да. Вот оно. Все понятно. Ну ладно.
Оно называется неправильно, но оно есть.
Угу. Похоже, что да. Написано в эфире.
Ну да, я открыл и сам себя там услышал.
Все, ну отлично. Спасибо. Okay, so our main goal for today is to discuss the notion of completeness for topological vector spaces. Well, first of all, before we define completeness, let's make a short digression to general topology, and let's talk about nets. Nets in topological spaces. Well, first of all, roughly a net is a generalized sequence indexed by an arbitrary directed set. And first of all, before we define nets, let's slightly generalize the notion of a partially ordered set. So we have the following definition. Partially pre-ordered set partially pre-ordered set is a pair consisting of a set lambda and a binary relation on lambda such that this relation is reflexive. Lambda is less than or equal to lambda, and transitive. Lambda is less than or equal to mu, and mu is less than or equal to, say, nu. Oops. Oh, I'm sorry. Well. Let's try this once again. Partially pre-ordered set is a pair consisting of a set and a binary relation lambda such that the relation is reflexive and transitive. So the difference between this definition and the definition of a partial order is that we don't require anti-symmetry. Sometimes this generalized notion turns out to be more convenient. For such sets, we can define the property of being directed in exactly the same way as in the case of ordered sets. So we say that a partially pre-ordered set lambda is directed if for any two elements lambda and mu, there is another element which dominates both lambda and mu. And from now on, by a directed set, directed set. By directed set, we mean a directed partially pre-ordered set.
What is a meaningful example of this without antisymmetry?
Excuse me?
Can you give an example with, of this without antisymmetry, which is reasonable?
What is reasonable? We may define, we may say that lambda is less than or equal to mu for all lambda and for all u.
Okay.
Maybe I'll give you a more useful example, which is useful in some questions of questions of general topology a bit later. So by directed set, we mean a partially pre-ordered set. In fact, in most cases, we may work with partially ordered sets. But sometimes this generalized notion is more convenient. Okay, so now suppose that X is a topological space. By definition, a net in X is a pair consisting of a directed set lambda and a map with legs from lambda to X. In Russian, instead of сеть, мы обычно говорим направленность.
Я обычно так и говорил.
По-русски?
Ну да.
Потому что сеть.
Ну или сеть.
Направленность как-то более принята в русской литературе.
У нас же везде вот эти все утверждения, которые переформулируют там Хаусдорфовость, замкнутость, они же вроде требуют отображения из... Ну,
да.
Нет, порядочно.
Да.
Простите, с антисимметричными, с нормальными отношениями.
Да.
То есть это не классическое определение сейчас.
Определение, the definition of a net can be given in the context of directed partially ordered sets. And in most cases it's reasonable. But there are some exceptions. So this is, the exceptions appear when we, so let me define convergence. Let's now recall what is a convergent net, and then I'll make some comments about this more general situation. Okay, so this is a net, and when we work with nets, we usually use the following simplified notation. Instead of writing x of lambda, we write just x sub lambda, and we think of a net as a family of elements of our space indexed by lambda. So in particular, if lambda is just the set of natural numbers, then x is just a sequence. X is a sequence. Okay, if we now have a net in a topological space, we can define convergence in exactly the same way as for sequences. We say that a net x lambda converges to x and write the following combination of symbols. If for every neighborhood u of x there is an element lambda 0 such that x lambda belongs to u whenever lambda is greater than or equal to lambda 0. And here's a typical example. We choose a point, x, in our space, and suppose that beta is a base at x, a base of opened neighborhoods of x. Then beta becomes a directed set with respect to the following order relation. So a neighborhood is bigger in the sense of our order relation if it is smaller, if it is a subset of the first net. So this is a directed set. And now for every u beta, let's choose xu in u. That it's immediate from our definition that xu converges to x. This is a typical example of a convergent net, which makes sense in any topological space. Another example. This example is exactly an example of a situation where lambda is not a partially ordered set, but is partially pre-ordered set. So let lambda consist of all pairs, say y and u, where u belongs to our base and y belongs to u. And we say that, so we must introduce the order relation. In order relation, we say that y1 u1 is less than or equal to y2 u2 by definition if u2 is contained in u1. This is a partially pre-ordered set, so this spectral relation is not antisymmetric. And now we can define a net if lambda is a point in our set. We let x lambda be just y here. And then it's clear that x lambda converges to x. This may seem a little bit artificial, but in fact it's useful when we compare two types of objects which may converge. Another approach to convergence theory is based on the notion of a filter in a topological space. I will define filters because we don't need them, but in fact filters are in a sense equivalent objects to nets. We may define convergence for filters, and we may define convergence for nets. And when we, if we want to prove the equivalence of two types of convergence, it is very useful to work with partially pre-ordered sets, which are not partially ordered, and with examples of this kind.
Equivalence of two types of
Convergence for nets and convergence for filters. Now, we will not need filters in our course, so for our purposes, nets are more in nature. Okay, the main advantage of nets, as compared to sequences, is that they encode the topology in our space. In the sense that once we know which nets converge, we can reconstruct the topology. And this follows from the following standard exercise. Suppose that y is a subset of x, and little x is a point, x, then x belongs to the closure of y, if and only if there exists a net, y lambda in y, such that y lambda converges to x. So this implies that we can, once we know which nets converge, we can reconstruct the notion of the closure of any set. So we can reconstruct the collection of all closed sets, and hence the collection of all open sets. That is the topology on X. Another example of the same phenomenon is the following criterion of continuity. Here we have a map between two topological spaces, X and Y. And this map is continuous at some point X, if and only if for every net x lambda in x such that x lambda converges to x, we have the following convergence of f lambda to f of x. This is a continuity criterion in terms of nets. Of course, if we work with metric spaces, then in both cases we may place nets by sequences, here and here. And more generally, this is true if x is first countable, that is, if every point has a countable base of neighborhoods. But in the general case, sequences don't work, and that's why we have to use nets. This is the main reason why we why we consider nets in arbitrary topological spaces, and why sequences are not, why sequences don't suffice. The notion of compactness can also be conveniently stated in terms of nets. So let's first give the following definition. We say that the point of our space is an accumulation point of a net x lambda if for every neighborhood u of x and for every lambda 0 in our set, there is a bigger element lambda such that x lambda belongs to u. And we have the following exercise. I claim that x is compact if and only if every net in x has an accumulation point. Again, in the well-known case of metric spaces, this here we can replace nets by sequences here, and this in this way we get the usual notion of sequential compactness. That is, every sequence has a convergent subsequence. But in the case of arbitrary topological spaces which are not metrizable, we have to work with nets here. Actually, we could define the notion of a subnet, but this this definition is not very intuitive. And that's why I prefer to work with accumulation points. Okay, let's now introduce completeness for topological vector spaces. Suppose that X is a topological vector space. And suppose we have a net x lambda and x. We say that this net is a Cauchy net. If for every neighborhood of 0, there is an element lambda 0 in our set, such that x lambda minus x mu belongs to u whenever lambda and mu are greater than or equal to lambda 0.
Excuse me, you don't need a notion of so-called strict accumulation point. You don't have problems with isolated points in this exercise.
Actually, I don't see any problems. Well, if you have some counterexample in mind, then please tell me. But accumulation point is what I've just written down here. So this is not a point in the closure. It's slightly different. Well, I don't see any problems. Okay. Okay. Well, so this is a general definition of a Cauchy net in the topological vector space. Well, let's look at some basic properties of this notion. So we have the following proposition. First of all, if our net converges, but it has a limit, x, then it is a Cauchy net. Second, if x lambda is a Cauchy net, which has an accumulation point, say little x, then it converges to x. Property 3 is that you have a continuous linear map, say phi is a continuous linear map from x to y, and x lambda is a Cauchy net in x, then its image will be a Cauchy net in y. Continuous linear maps take Cauchy nets to Cauchy nets. Property 4 characterizes Cauchy nets in terms of seminorms. If X is a locally convex space, and P is a defining family of seminorms on X, and then X lambda is a Cauchy net, even only for every seminorm P from our family, and for every positive epsilon, there is an element lambda 0 in our set such that P of x lambda minus x mu is less than or equal to is less than epsilon, whenever lambda and mu are greater than or equal to lambda 0. But the proof is quite straightforward, so this is an exercise for you. Okay, so now suppose that X is Hausdorff topological vector space, and S is an arbitrary subset of X. We say that S is complete. S is complete if every Cauchy net in S has a limit in S. Well, formally we could define the same notion for arbitrary topological vector spaces, not necessarily Hausdorff, but for technical reasons it is much more convenient to work with Hausdorff topological vector spaces. Well, the reason is that if we, for example, define this notion for arbitrary topological vector spaces, then there will be some problems with completions. So if we want to prove the existence of a completion, then we must require X to be Hausdorff. Okay. Well, of course, you know what a complete metric space is. So the natural question is how these two types of completeness are related to each other. I mean, completeness for metric spaces and completeness for subsets of topological vector spaces. Well, I try to answer in a few minutes. And let's now make some simple observations concerning completeness. First of all, if S is a complete subset of X, then it is closed. Because it is otherwise, if it is not closed, then we can choose a net in S which converges to a point which doesn't belong to S. And this will be a Cauchy net which has no limit in S. Property 2, if S is contained in another set T, and T is complete, and S is closed in T, then S is complete. This is also needed from the definition. And property 3 is that every compact set is complete. Well, indeed, if you take a Cauchy net in a compact set, then by compactness it has an accumulation point. But a Cauchy net which has an accumulation point converges. Where is it? It must be here. Yeah. A Cauchy net which has an accumulation point converges. So this implies that every compact subset of a topological vector space is complete. Okay, let's now look at the following simple but important result, the so-called extension by continuity theorem. Extension by continuity. Suppose X is Hausdorff over X. This can be any topological vector space. This is a topological vector space. And X0 a dense vector subspace. And also suppose that we have a complete topological vector space Y. Let's draw a picture. So this is X0, this is X, and this is Y. I claim that for every continuous linear map phi 0 from X0 to Y, this is phi 0, there is a unique continuous extension. There is a unique continuous linear map phi from X to Y, which extends phi 0.
And for nonlinear maps, this result fails.
Fails, yeah. The uniqueness is true, but the existence. The uniqueness is true, but the existence essentially assumes that phi 0 is linear. The proof is actually exactly the same as in the case of normed spaces. So this is an exercise for you. Proof is similar to the case of normed spaces. The difference is that we will take the standard proof for normed spaces and we replace sequences by nets. We take a point in X, we choose a net in X0 which converges to this point. This will be a Cauchy net because it converges, but it is a Cauchy net in X0, so phi 0 takes this Cauchy net to a Cauchy net in Y. But Y is complete So it converges to some limit in y, and we take the original point here to this point little y. And this defines our map phi. And then we have to prove that this map is well defined, that it doesn't depend on the choice of the set here, and it is linear and continuous. So this is not very difficult, but it requires some standard work, which you have probably already done in the case of norm spaces in your course of functional analysis. Okay. Okay, let's now discuss how completeness of topological vector spaces is related to metric completeness. Theorem. Suppose X is a metrizable topological vector space. And let rho be a shift invariant metric on X, which generates the topology of X. How about the existence of this rho? Well, we have actually proved the existence of such a metric in the case under the assumption that X is locally convex. In the general case, this is also true. I don't remember if I gave you this exercise explicitly, but in fact, if you have an arbitrary metrizable topological vector space, not necessarily locally convex, then its topology can be given by a shift invariant metric. So anyway, we assume that rho is such a metric. Then the following conditions are equivalent. Condition 1, X is complete. Condition 2, X is sequentially complete. Which means, by definition, that every Cauchy sequence converges. Every Cauchy sequence converges. And property 3, X is complete as a metric space with respect to rho. Again, the proof is an exercise for you. In fact, the only point which is not entirely trivial is to show that 2 implies 1. Clearly 1 implies 2, this is obvious. And it's very easy to show that 2 and 3 are equivalent, because rho is shift invariant. So if we look at our definition of a Cauchy net, so assume for a moment that this is not just a net but is a sequence, well, this means that if lambda and mu are big enough, then this difference belongs to u. But if u is a ball, say of radius epsilon, this means exactly that the distance between x lambda and x mu is less than or equal to is less than epsilon. And we get the usual definition of a Cauchy sequence for the metric rho. So this implies that 2 and 3 are equivalent. And the only point which is not entirely trivial is to show that 2 implies 1. But this is not very difficult. You just choose a countable base of neighborhoods of 0, say un, and by using this countable base, you construct an auxiliary Cauchy sequence in X, which converges by sequential completeness, and then prove explicitly that the initial net converges to the same limit. Well, this is a rather standard argument, which is more or less the same as in the case where you prove that if, say, in a metric space, if you have a Cauchy sequence, which has a convergent subsequence, then the initial sequence also converges to the same limit. Here we work with nets, but the situation is very similar. Okay. So anyway, so we have so now we have two kinds of completeness: completeness for metric spaces and completeness for subsets of topological vector spaces. We see that they are compatible in the sense that this theorem is true. But nevertheless, it's obvious that none of them is a special case of another, because, well, a topological vector space is not necessarily metrizable, and on the other hand, if we start with a metric space, then this metric space has no linear structure, and it is not embedded into any topological vector space. In fact, both types of completeness, I mean completeness for subsets of topological vector spaces and completeness for metric spaces, both of them are special cases of completeness for more general objects, the so-called uniform spaces. So roughly, a uniform space is a topological space together with an extra structure which enables us to compare neighborhoods of different points. For example, if we work with a metric space, we may compare balls with different centers simply by comparing their radii. So this one is bigger because its radius is bigger than the radius of this one. When we work in a topological vector space, we can compare neighborhoods of different points by using translations. So on my picture, this neighborhood is smaller than this one, because if we translate both of them to 0, if you translate both of them to 0, then, well, this is x, this is y, then this one will be smaller than this one. Where is it? Oh. The number of corrections is limited. Okay. Anyway, in a general topological space, there is no way of comparing the neighborhoods of different points, but this is possible in uniform spaces. So a uniform space is a topological space with a certain extra structure which enables us to compare neighborhoods of different points. And it turns out that in a uniform space, you can define, for example, uniformly continuous functions or equicontinuous families of maps between uniform spaces. You can define Cauchy sequences and Cauchy nets in any uniform space. And you can introduce the notion of completeness for uniform spaces. Well, anyway, all these objects are too general for our purposes, so we will work with completeness for topological vector spaces and for their subsets. Okay, so let me reconstruct part 3. Part 3 was that X is complete for this metric rho. Okay. By the way, it's of course it's essential here that rho is shift invariant. Because if it is not shift invariant, then, well, you will easily produce a metric on the real line, which generates the same standard topology of the real line, but which makes the real line into an incomplete metric space. So the shift invariance is essential here. By the way, there is a special name for such spaces. They are called Fréchet spaces. Fréchet space is a complete metrizable locally convex space. And we will see soon that many classical results many classical results about bound spaces hold in the more general setting of Russian spaces. Okay, let's now look at some constructions which preserve completeness. Proposition 1. Proposition 1. You have a family, Xi, a family of locally convex spaces. Then the product is complete, if and only if all of them are complete. In fact, this can be easily generalized to arbitrary topological vector spaces, but for convenience, let's work on with locally convex spaces only. The proof is again a simple exercise for you. In particular, we see that the space of all functions on an arbitrary set, say set X, S, so S is a set, is complete. Proposition 2, suppose that we have a projective system, of locally convex spaces, of complete locally convex spaces. Let's recall that their projective limit exists and can be identified with a certain vector subspace of their product. So I claim that this vector subspace is actually closed in the product. Is a closed subspace of the product. And since we already know that the product is complete, we conclude that the projective limit is also complete. Projective limit of complete spaces is complete. Which is, by the way, a very useful way of proving completeness. Where we'll see some examples very soon, which illustrate this proposition. Again, the proof is very easy, and this is an exercise for you. Before discussing other constructions, okay, so before we discuss other constructions, let's look at the following standard trick of proving completeness. This is not a theorem, but this is a very useful trick. So suppose we have a locally convex space X, and suppose we want to show that it is complete. Assume that there exists a complete locally convex space Y, complete locally convex space, and a continuous injective map, a continuous linear injective map from X to Y. Continuous linear injection. So we take a Cauchy net, X lambda, Cauchy net X, and since this embedding is a continuous linear map, we see that the same net will be a Cauchy net in Y. But Y is complete. So this implies that X lambda converges to some point in Y. And now to complete the proof, we have to show that, first of all, this little y actually belongs to x, and second, that x lambda converges to y for the topology of x, which is in general stronger, but it's finer than the topology induced from y. But this is a rather general setting. And actually, you are already familiar with this setting. So an illustration of this trick. Standard illustration is the standard proof of the completeness of little LP. The little LP space. If you look at the standard proof of the completeness of the space, you will readily observe that actually it is based on the same trick. LP is embedding into the space of all sequences. This is a continuous linear injection. This one is complete. So you apply the same trick, and by using some little calculations, you show that this limit actually belongs to LP, and the original sequence converges to this limit for the LP norm.
But unlike in magic spaces, we don't have a universal thing which we can embed it to, right? In magic spaces, we
universal.
In double star. In magic spaces, we always can embed it into double star.
Yeah, double star doesn't work in the case of locally convex spaces. We'll see why it doesn't work when we discuss reflexive, semi-reflexive spaces and so on. In general, double star, the topology, there is an embedding of x into x double star, but the topology induced from double star is stronger than the original topology of x. The double star space is not necessarily complete. So it simply doesn't work for locally convex spaces.
So we don't have anything that we can, we don't have a universal way to embed the locally convex space to somewhere.
Yeah, we do have a universal way, but it is not based on the geos.
Ну, у нас есть в метрическом случае еще так называемая бесконечность конструкции.
If you mean completion, we'll discuss completions fairly soon, and it is indeed universal in some sense. The difference is that we cannot use dual spaces and bidual spaces to define completions. But the construction itself, the construction of completion exists in the context of topological vector spaces. Okay, let's now look at other constructions. I forgot the numbering. This was proposition 2. Okay. Now proposition 3. Proposition 3. You will have a family Xi, a family of locally convex spaces. I claim that their locally convex direct sum is complete, even only if all of them are complete. So in some sense, the situation is the same as the case of products. The proof is again an exercise for you, but it is not so straightforward as in the case of product. As in the case of products, so I'll give you a hint. To prove the completeness of the locally convex direct sum, you apply this trick to the inclusion of the locally convex direct sum into their product. And use the trick. This one is complete. You take a coordinate here and follow this follow this way. Okay. How about quotients? Well, in general, the answer is no. The quotient of a complete space is not necessarily complete. But everything is okay if we work with Fisher spaces. Proposition 4. Proposition 4. If X is a Fisher space, that is a complete metrizable locally convex space, X0 is a closed vector subspace, then the quotient of X modulo X0 is a Fisher space. And here's, well, not just a proof, but an idea of proof. Sketch of proof. Clearly, the quotient is metrizable. It is Hausdorff because X0 is closed on X. And since X is metrizable, the topology on X is generated by countably many seminars. So the quotient seminars generate the topology on the quotient. There are countably many of them, so the quotient is metrizable. Well, we have to prove completeness. We have to prove the completeness for the quotient. And so to begin with, we choose a sequence, a defining sequence of seminars on X. Let's denote the seminars like this. A defining sequence of seminars on X. We may easily make it increasing, but just by taking first take any countable family and then take the maximum of the first one and the second one, then the maximum of the first one, the second one, and the third one, and so on. And in this way, we get an increasing defining sequence of seminars. So we take a Cauchy sequence, U, K, Cauchy sequence in the quotient. And without loss of generality, we may assume that the following inequality holds: uk plus 1 minus uk, so the kth seminorm is less than 1 over 2 to the power k. If of course, an arbitrary Cauchy sequence doesn't have to satisfy this inequality, but we can find a suitable subsequence satisfying this condition. Then we choose, and we do the following. First of all, we choose an arbitrary element, an arbitrary representative of U1, any x1 belonging to U1. And now we use induction. And if x1 up to xk are already chosen, we choose xk plus 1 in uk plus 1 in such a way that the following inequality holds. So here, this is, I didn't say this explicitly, but here, of course, I mean the quotient seminorm on x modulo x0. The quotient seminorm or the kth seminorm on x. So we get, as a result, we get a sequence of elements of x, which is obviously a Cauchy sequence. This inequality implies that xk is a Cauchy sequence in x. So it converges to some element level x. And so this implies that uk converges to x plus x0 in the quotient. And that's it. So the quotient of a Furche space modulo a closed vector subspace is also a Furche space. And now a warning. In a general case, if we start with a complete locally convex space and a closed vector subspace x0, closed vector subspace, this doesn't imply that the quotient is complete. Some counterexamples will be included in the next exercise sheet. Okay, how about inductive limits? Well, we already know that inductive limits, in general, they are badly behaved. At the previous lecture, we constructed an inductive limit of a sequence of Banach spaces, which is not Hausdorff. And so it cannot be complete. But on the other hand, we have the following fact. The strict inductive limit, of a sequence of complete locally convex spaces is complete.
Strict is when all our maps are terms.
Or, yeah, logically injective. Yeah, this is not entirely trivial. The proof will be given later after we discuss completions. Okay, let's now look at some concrete examples of complete locally convex spaces. Example 1, if X is a locally compact Hausdorff topological space, then we know that the space of continuous functions on X is isomorphic to the projective limit of the spaces of continuous functions on compact subsets of X. This was discussed some time ago, 2 lectures ago, if I'm not mistaken. So C of K is a Banach space, of course, for the supreme norm, and we know that the projective limit of complete spaces is complete. And so this implies that C of X is complete. And if moreover we assume that X is second countable, moreover X is second countable, that is, has a countable base, then we know that in this case C of X is symmetrizable, and so it is a Furche space. Example 2, let's take an open subset of Cn. Then the standard exercise in complex analysis is to show that the space of holomorphic functions on U is closed in C of U in the space of continuous functions. Well, let's assume for simplicity that n equals 1. If you're familiar with analysis of several complex variables, you can easily extend this to arbitrary n. But if n equals 1, then this is a more or less standard fact of complex analysis. And so this implies that since C of U is a Furche space, we conclude that the space of holomorphic functions is also a Furche space. example 3, let's now look at spaces of smooth functions. Suppose that U is an open subset of Rn. And let's take a compact exhaustion, MP, a compact exhaustion of U, such that each MP is a smooth manifold with boundary. For example, if U is just Rn, then you can take the sequence of open balls. Then, if we look now at the space of C infinity functions on U, then this will be isomorphic to the projective limit of the spaces of CP on MP. This was discussed in detail in the case of the real line 2 lectures ago. And so, since this is a Banach space for the natural norm, so we see that C infinity of U is a projective limit of Banach spaces, and so it is a Fisher space. Example 4. If we take the space little s of rapidly decreasing sequences, or for example the Schwarz space on Rn, or we can also take the space of holomorphic functions considered in example 2. I claim that all of them are countable projective limits of Banach spaces. Are countable projective limits of Banach spaces. This is actually an exercise for you, but the details were already discussed some time ago. For example, some time ago we explicitly constructed such projective sequence for the space little s. So this implies that they are Fisher spaces. They are Fisher spaces. Example 5. Okay, let's now look at some strict inductive limits. If we take the space of continuous compactly supported functions on a second countable locally compact topological space, second countable locally compact space, or we can take the space of smooth compactly supported functions on an open subset of Rn. So these spaces are strict inductive limits of sequences of Fisher spaces. Strict inductive limits of sequences of Fisher spaces. This was discussed at the previous lecture. Actually, the first one, the space of continuous compactly supported functions, is a strict inductive limit of Banach spaces. And this one is a strict inductive limit of Fisher spaces. Anyway, it follows from our general fact, which wasn't true so far, that they are complete. They are complete. Another standard space in our list of concrete locally convex spaces is the space of holomorphic germs. which is an inductive limit of Banach spaces, but which is not a strict inductive limit. It turns out that this space is also complete. Space of holomorphic germs at a point on the complex plane is complete for the following reason. We may take this space. Actually, the same argument applies to these two spaces. The spaces of continuous or smooth compactly supported functions. So all of them are projective limit, but now uncountable. Projective limits of Banach spaces. This is an exercise which is, by the way, not entirely trivial. It is maybe a little bit surprising because all these spaces are constructed as inductive limits. But at the same time, it turns out they are projective limits of Banach spaces. And so this implies that they are complete. Well, here's a hint. If we consider the spaces of smooth or continuous compactly supported functions, then to prove that they are isomorphic to projective limits of Banach spaces, it is convenient to use explicit defining families of seminorms from exercise sheet 4. Use concrete families of seminorms. Three or four, I don't remember actually. And if we take the space of holomorphic germs, to prove the completeness, use the following argument. You have a power series of the following form. Now the series has a positive radius of convergence. That is, represents a holomorphic germ. Even only if the following sum is finite. For every sequence Pn of positive numbers, such that well, the growth of Pn is exponential in the following sense. Not the growth, but the decay of Pn is exponential in the following sense. This is little o of epsilon to the power n for every positive epsilon. So I recommend you first to prove this equivalence, and then to guess how this equivalence implies the fact that this space of holomorphic germs can be represented as a projective limit of Banach spaces. Okay. Now, actually, another example, and an exercise at the same time. We have already met the notion of sequential completeness in the context of metrizable local economic spaces, and I claim that in this case, sequential completeness is equivalent to the completeness. But in the general case, this is not true, and here's an example.
In which case?
In the metrizable case. So we take an arbitrary uncountable set, yes, uncountable set, and we let X be the space of these functions on X, such that f of S is 0 for all but countable many points. This is a subspace in K to the power S. So the exercise is to show that X is sequentially complete, but is not complete. This is very similar to the well-known example of a topological space which is sequentially compact but is not compact. This is very similar. Okay. Okay, let's now talk about completions. Again, for simplicity, we will consider completions in the context of locally convex spaces. But in fact, this notion makes sense for arbitrary topological vector spaces. So suppose that X is a locally convex space. By definition, the completion of X is a pair X tilde and J, where X tilde is a complete locally convex space, and J is a topologically injective linear map, such that the range of this map is dense in X tilde. Oh, sorry, this is not. This is reasonable, but since I'd like to give a definition which applies to locally convex spaces which are not necessarily Hausdorff. So let me give a definition in terms of a suitable universal property. Sorry. So J is just a continuous linear map. Continuous linear map such that the following universal property holds. So this is X, this is X tilde, this is J. So such that for every complete locally convex space Y, this is Y, and for every continuous linear map, say phi, from X to Y, this is phi, there exists a unique continuous linear map phi tilde from X tilde to Y, this is phi tilde, such that the diagram commutes. The same definition can easily be given in the context of categories. So let's denote by CLCS the category of complete locally convex spaces. This is a full subcategory of locally convex spaces consisting of complete spaces. Subcategory consisting of complete spaces. Then the same definition can be given in the following equivalent form. Definition prime. The completion of X is a complete locally convex space X tilde, this one, together with the following nature isomorphism. between continuous linear maps from x to y, and continuous linear maps from x tilde to y, where y runs over the objects of CLCS, that is, over complete locally convex spaces. And it's simple exercise to show that the definitions are equivalent. It's easy to deduce from the definition that if a completion exists, then it is unique. A remark, which is more or less immediate from the definition, about the uniqueness of completion. You have two completions of the same space X, say X tilde and X hat, together with the respective maps from here to here and from here to here. Then there exists a unique topological isomorphism between the completions, which makes the diagonal commute. This is immediate from our definition. First, you take an arrow from here to here by using the definition. Then you get an arrow in the opposite direction, again by using this definition. And then the uniqueness implies that the composite map is the identity map in both directions. Okay, this is more or less obvious, the uniqueness, but now how about the existence of the completion? It's much more interesting. And the first step, which will be the last step for today's lecture, is to reduce everything to the case of Hausdorff spaces. So let's make the following observation. Suppose that X is a locally convex space, which is not necessarily Hausdorff, and let xh denote the quotient of x modulo the closure of 0. Well, 0 is of course a vector subspace of x. It's easily seen that the closure of a vector subspace is also a vector subspace. So we quotient out the closed vector subspace, the closure of 0, and we get a Hausdorff locally convex space. xh is a Hausdorff locally convex space. And xh is called the Hausdorff space associated to x. Hausdorff locally convex space associated to f. To x. Let's now observe the following. First of all, the associated Hausdorff space has the following universal property. For every Hausdorff space Y, we have a one-to-one correspondence between continuous linear maps from xh to y and from x to y. For all Hausdorff locally convex spaces Y. So here, as before, by HLCS, I denote the category of Hausdorff locally convex spaces. Well, indeed, why is it true? If you have an arbitrary continuous linear map from x to y, where y is Hausdorff, then this map vanishes at 0, and by continuity and by the assumption that y is Hausdorff, it vanishes on the closure of 0. And so it factorizes through the quotient of x modulo the closure of 0, and we get the map from here to here. And this is easily seen to be one-to-one correspondence. And the second observation is that to construct the completion of x, it suffices to construct the completion of xh. More exactly, if suppose that we have a complete locally convex space, x tilde is a complete locally convex space, and J is a continuous linear map from xh to x tilde. I claim that x tilde together with J is a completion of xh even only in the same space, x tilde, together with the respective map, J composed with Q, where Q is the quotient map, QH is the quotient map of X onto XH. So even only if this pair is a completion of X. Well, this is actually needed from the definition and from observation 1. So indeed, if we have a let's look at our diagram. For example, if you want to prove that x tilde is a completion of x by using this definition, we simply take an arbitrary continuous linear map from x to y, where y is a complete locally convex space. Then by using the universal property of xh, we factorize this map through xh, and we get map from here to here. And now, since x tilde was assumed to be a completion of xh, we can further construct a map from here to here, such that the upper triangle is commutative. And as a result, if we now look at the whole picture, we see that x tilde will be a completion of x. And actually, they are going around. So as a result, we see that the problem of constructing the completion reduces to the case where our space is Hausdorff. And at the beginning of the next lecture, we will see how to construct a completion for Hausdorff locally convex spaces. And that's all.